we are going to dive into correlation and talk about how it might help us with prediction. Let us back up for one tiny second, however, and say, why are we doing data science? So there are four big reasons. I do accept more, but let's start with just these four. Number one, we want to know what's going on in the world. What's happening, right? So, for example, a couple of people around the world may be asking, are temperatures rising? We can look at some data and say, wow, the global average temperature from 1850 to 2018 seems to have gone up. All right. We also might do data science because we want to explain why is something happening. For example, why are temperatures rising? There's a big old fight out there, if you're not aware, about what's causing that. We'll set that aside for now. We might be interested in policy evaluation. What effect does some policy have, such as a ban on plastic bags? Will that make a difference for global average temperatures? What if we did it worldwide? We could use data science to start to answer those things. We also may want to predict. In fact, this is one of the areas that people tend to be most jazzed about when it comes to data science, though I will argue that the first three are super valuable. Most companies that are implementing data science that I have seen, selection bias here, do a lot of observation and then they jump right into prediction. And it's not to say that you have to do all four of those in order. I just think that there's a lot we can learn in steps 1 and 2 there that we tend to overlook. That said, we're going to jump right into prediction today. All right, so we might wonder, how will a 2% increase in global temperature affect sea levels? That's something that may be crossing your mind. As someone in New York City, I think about this sort of scenario more often than I'd like to. Prediction is everywhere. It's on television. This dude tries to make some predictions every now and again. Anytime you turn on Netflix, Hulu, Amazon, whatever, and they suggest things, they're doing so because they are predicting what you might like. If you're taking medication, you are effectively interpreting a table of prediction. I am predicting that a child of such and such weight is going to need such and such amount of drugs. And of course, we're making predictions about things that we care about, for example, deforestation. So, one starting point for prediction is association. Generally, all we mean is how two variables go together. We could have a positive linear relationship, we could have a negative linear relationship, and lots of other types of relationships that are not linear. And of course, no relationship at all. Generally speaking, when we start thinking about association and other ways that variables go together, we tend to start with linear relationships. So, linearity is just a way of saying that a relationship can be graphically represented by a straight line. And I will even add to that, graphically represented in a straight line in a way that feels true to the thing we're measuring. And that's super feely. People don't come to data science expecting to feel things, but strap in. So this scatter plot shows pro-life attitudes among Americans and attitudes that support gun restrictions in the United States. Shout out to Professor Arthur Sperling, one of my co-instructors for this course, for this example. And it turns out the more pro-life someone is, the less likely they are to support gun restrictions. This is probably a very unremarkable finding if you've seen the news in your lifetime. So it looks like a negative relationship. I can start to say some predictions, right? I can say, if I know that someone is more pro-life, I might also know that they are less favorable of gun restrictions. If we assume this is a linear relationship, that means drawing a line through this scatter plot accurately conveys roughly how we think about the relationship between these two variables. Okay, so we can make some predictions in a general sort of sense. But is this a linear relationship? If you saw me draw that green line through that graph, you probably winced just like I did on the inside. So many emotions today, right? Is this the best fit line? Is this really capturing what Americans think? Is it really capturing what this scatter plot is demonstrating? I can't even help myself. I'm already drawing the curve that I think fits better. So really a curve more in this shape. This is probably a non-linear relationship. At this point, many of my students in my NYU course, when I taught this, would say, what's the rule? How do we know which it is? And for now, we're leaving it as take a look, see what you think. All right, so let's look at a few other examples. So this is a relationship between support for Obama and whether or not someone is pro-choice. This seems positive, and I would argue we can get away with claiming that it's linear. Here's another example. This is the relationship between the population in a country and the unemployment rate in that country. Seems positive as well. As population goes up, we see unemployment rates go up, and vice versa. But I would argue that the best fit line through this scatter plot is probably more of a curve. Now, these are just rough estimates. I'm eyeballing these things, but I want you to start to get an intuition for, are we working with a linear relationship or not? One of the reasons that I'm belaboring this point is a lot of the work that we're going to do both in correlations and later in linear regression is going to assume at the outset a linear relationship between our variables, it's possible and frankly quite common to violate that assumption, which means our linear regression and our correlation coefficients are maybe not so informative. If that's the case, we need to think about other techniques. But one thing to be on the lookout for out there in the big wide world is people doing correlation and linear regression for relationships that are not linear. So early on, I want you to develop instincts to say, I'm looking at a scatter plot. Does this seem linear or not? And we've also seen in this example that we can learn a lot from just plotting. We just made some simple scatter plots, right? We were able to infer things like the direction of the relationship between X and Y. We made some decisions about the linearity. We understood a little bit about the strength of the relationship. So, how reliably, if you increase X, does Y increase a lot? Does Y increase a tiny bit? That's a helpful thing to know. But we haven't been formal. We're using the world famous ocular method, looking at. We haven't quantified anything. We haven't put any numbers around it, but we can. Oh, amazing. I'm so glad you are here. Let's add some numbers. So, plots are good. Plots are great, but we want a measure. So, a measure of linear association could tell us how well that straight line fits the relationship between two variables. Ooh, lovely, right? It can tell us about the strength of the relationship between those variables, and it can tell us about the direction. Is it positive, negative, neutral? We are going to use correlation coefficients. Correlation coefficients are going to tell us those things about our association. So you can think about correlation as a type of measure of association. Students often are like, which is which? So association, generally, do they go together? Correlation is one way to quantify an association. All right, so the correlation coefficient, which is what we're going to be working towards, measures the linear association between two variables. We write it as a lowercase r, and we'll see this r again in a slightly different form. Suspense, oh my gosh. R can take on the values from -1 to 1. If you see a correlation coefficient of -1, two variables are perfectly negatively correlated. In real life, a true -1 correlation is rare. If you see one in the wild, please tell me immediately. Wake me up. I don't care what hour it is. I need to know. If a correlation coefficient is 1, two variables are perfectly positively correlated. Generally, we're going to be working in a world where we have strong associations or maybe even weak associations. And of course, we also want to be on the lookout for no associations, which would be when R takes on a value of 0. So get comfortable eyeballing these sorts of types of scatter plots. These images are taken with gratitude from the Data 8 textbook from UC Berkeley. Go to inferentialthinking.com and you can look at some code for how they generated these scatter plots. But generally speaking, you don't need to be able to spot identify. There's not like perfect pitch, but perfect correlation coefficients. You're like 0.9, 0.87. You don't need to do that. Students often panic like, oh my God, do I have to be able to look at these and tell you exactly the correlation coefficient? No, but build an intuition for, oh, okay, if it's negative and it seems like the scatter plots are pretty tightly placed around what would be that line, then we're probably in a strong negative linear correlation. How do we calculate this? There are a lot of different types of correlation coefficients out there. One of the more common ones is the Pearson's correlation coefficient. We calculate Pearson's correlation coefficient by merely taking the average of the sum of the cross product of the z-scores. Now, this course is more focused on building a high-level intuition, and so I'm going to use that as an excuse to not spend time on this. We do talk about this in more detail in the corresponding free online textbook. I'll put a link to it in the video notes. Correlation is really useful. It gets a bad rap. We have a lot of correlation is not causation. We might as well put it on t-shirts and fortune cookies. It's not causation, but that doesn't mean we can't learn things. Correlation is really useful. It's unitless. I like this about correlation. It has no units. This allows us to compare correlations from seemingly unrelated things. So the relationship between literacy rates and happiness and the correlation between horse height and GDP in a country. We could say, which of these are more tightly correlated? Wonderful. I can think of all kinds of amazing examples. I truly can. Linear rescaling of variables also doesn't affect correlation. For example, the correlation between temperatures in New York City and Boston are the same, regardless of whether I measure it in Celsius or Fahrenheit or degrees Kelvin or what have you. The correlation between X and itself is 1. Correlation is also symmetric. The correlation between X and Y is the exact same correlation as that between Y and X. We like this. Now, we already know correlation is not causation. Yes, fine. It's a kind of association. We know this. All right. It could be spurious. You can find correlations between all kinds of things that we don't really have a theoretical reason to assume are related, such as this. But we still can learn things, as I keep insisting. It's also a measure of linear association, as we started this video saying. So it really breaks down when our variables are not linearly associated. And this is very simple, but it's very frequently overlooked when we get out in the world because correlation is very easy to calculate in Python and any other programming language that we might use. We tend to assume linear correlation will work. In many cases, it won't. So here's an example of nonlinear correlation where we can't really use Pearson's correlation coefficient to make sense of any kind of linear association in a meaningful way. So here's a graph. The idea here, and you've all probably experienced this yourselves, as we get more and more anxious and more stressed out, we actually can become better performers. So we might rise to the occasions. But too much stress can then cause our performance to get worse. And I think we all can think of examples in our lives, whether it's taking a test, playing sports, any kind of performance. This is the relationship. It is not linear, right? So there is a relationship between stress and performance, but because it's nonlinear, we see a correlation of 0, which would not really represent what's going on in the world. Correlation is a measure of linear association. All of these relationships that we see right here have the same correlation. So when you are working with correlation, I urge you, not just to calculate the correlation coefficient and call it a day. Plot a scatter plot, take a look and say, gosh, am I actually capturing a linear relationship? There are ways of measuring nonlinear association. We will not be covering that in this course. So I have argued all along that correlation is not maybe appreciated as much as it ought to be. So it is helpful for association in the sense that it can help us say how two variables go together, which can help us predict generally. I think calculating a good old correlation, even if there isn't a causal relationship, could help us make predictions about the world and about things that we care about. There, I said it. Come at me. But it doesn't get that much more specific, right? We can say, oh, if X goes up, I can anticipate that Y will go up or down or whatever. If we want to do a little bit more than that, maybe we want to obtain a predicted value of Y for every X that we could be given. If X is 7, what do we predict Y will be? Maybe if we want to talk about the effect of a unit change on Y, if the temperature, global average temperature goes up by 1 degree, what will the effect be on sea level? Then we want to live in the world of regression. And that we will talk about in the next video. See you there.